Alright, how about a video with very little math? A whole lot of shapes going on. Yeah, that sounds like a good idea. Titration curves. Strong acid, strong base, not too interesting. I mean, interesting, you can get some information from it. But weak acid, strong base, or weak base, strong acid, that's what we're talking about. We get quite a bit of information. And the punchline is this. Oh, the first slide has the punchline. We have to learn how to apply it. If you have equal amounts of acid and conjugate base or base and conjugate acid, or if you're halfway into a titration, exactly halfway, then you know the pH has to equal the pKa or the pOH has to equal the pKb. When you first hear about this, like, what are you talking about? That's why we have to look at a whole bunch of examples. You could think about the Henderson-Hasselbalch equation if you want to. pH equals pKa plus the log of A minus over HA or whatever. But if that ratio, the log ratio is 1, that means you're halfway in the titration point, then the pH equals the pKa or the pOH equals the pKb. Either way. So let's look at some titration curves. Here are three acids represented on the same graph. Three acids, right. One of them's HF, one of them's KHP, one of them's HOCl. Which one of these three is the strongest acid? Yeah, you're right, it's HF because it's the lowest. It doesn't rise very quickly like a strong acid HCl would be, like starting here and then just come straight on almost perfectly flat until you reach this point right here, and then it would jump up drastically. And the weaker your acid, like HOCl, the more quickly it rises as you're titrating to the bump point right there. So I could make I could make a buffer from any of these situations, a different buffer from any of these situations, and yet a different buffer from any of these situations. Although you're pushing it with HF because it doesn't rise quite as quickly. HF is all complicated, all kinds of complicated. But in any case, if the equivalence point was about 25 milliliters, 24, 25 milliliters, half 25 is 12 and a half. So right about here somewhere, for this acid, the pH equals the pKa at the halfway point. So looks like the pH here is about 3, so the pKa must be about 3, and therefore the Ka is 10 to the negative 3. Here the pH is about 5-ish, so the pKa must be 5 and the Ka must be 10 to the negative 5. And here the pH is about 7 something, 7.5. So the pKa must be 7.5 and the Ka must be 10 to the negative 7.5. Interesting. And that's true all the time. By that I mean that pattern holds. So whatever your weak acid, this is kind of distorted in the y direction I think, but if my volume for the equivalence volume is 10 milliliters, it doesn't even matter. You don't have to know what the concentration of your base is. You don't even have to know what the concentration of your acid is. All you have to know is how much base it took to cancel the acid. Then I know the pH at that halfway point was equal to the pKa, 6.2-ish, and yeah, whoa. This seems like it's trickery or something, but it's not. It's always true. So if my equivalence volume is 10 milliliters, half that is 5 milliliters, doesn't work with a strong acid, but a pH of 4 gives a pKa of 4 halfway, so this is the stronger acid, and the weaker acid, and the weakest acid has a pH of 10 at the halfway point, and the Ka would be 10 to the negative 10. 10 to the negative 10 is a pretty weak acid. Similarly for weak bases. Strong bases doesn't work so well for, but if this is a pH of 10, the pOH is 4, 10 plus 4 is 14, and the pKb is 4, and the Kb is 10 to the negative 4. Interesting, yeah. These are some useful graphs, I really think they are. Back to the weak acid being titrated by the strong base. Again, halfway, if this is the full equivalence, that's a half equivalence. For this purplish colored curve, the acid has a Ka of about 10 to the negative 4.5. For the greenish curve, this acid has a Ka of about 10 to the negative 7, and the pH equals the pKa, 10 to the negative 9.1ish or whatever. Oh, there are the values right there. Interesting. And more examples. Do you need more examples? I got a whole bunch more to show you. So again, there's something very special about the halfway point of a weak acid titration or a weak base titration, and that namely is that the pH equals the pKa, or the pOH equals the pKb, if you're talking about a base. Which of these is the weakest acid? Which of them is the strongest acid? And why do we care about, let's see, this, oh geez, why'd they do this? It looks like the equivalence point for all these acids is right about, what, 16 or 17? So half of that, half of 16 milliunits is about 8, so go right about here, and then go up and say, okay, so this is halfway point. My pH is about 3 here, 3, so my Ka must be 10 to the negative 3. Whoa, interesting. So the acids get weaker as you move up this way. And that works, believe it or not, for a polyprotic acid. So if it took 30 milliliters to titrate totally, 10 milliliters to here, 20 milliliters to here, 30 to the whole way, then this pH of about 3 something, 3.5, that would be equal to the pKa1, and the Ka1 would be 10 to the negative 3.5. And if this is the second hydrogen ion and the second constant, oh yes, I made a mistake. So 10 milliliters the first equivalence point, 5 milliliters second equivalence point. Here the pH at the halfway point, halfway to this first equivalence is 2, and the Ka would be 10 to the negative 2. And the same thing here, to this halfway point between this equivalence and this equivalence, that halfway point is about, well, I don't know, what, 5 something? So the Ka2 would be 10 to the negative 5, and same for here, halfway in between this one and this one is the Ka3 at a pH of about 9-ish, so 10 to the negative 9 would be the Ka3. Have you thought about the stepwise dissociation of polyprotic acids and the constants that might explain that? What's the Ka2? Okay, Ka2, pH equals pKa, the halfway point, and 7.2. How about 10 to the negative 7.2? What's 10 to the negative 7.2? I think it's about this answer right here. I guess this is true, but kind of confusing. This is a diprotic acid, so one titration happens here, second titration happens here. Halfway to the equivalence point is this, and the pKa1 is that, and the pKa2 is that. Equivalence point 1, equivalence point 2. Alright, I can kind of buy it. That's the titration of the weak acid carbonic acid with NaOH. Yeah, I'll buy it. Whoa. Do I really want to go here? I don't know if I do. Think about it. It's a tricky one. This is phosphoric acid. At a very low pH, phosphoric acid is totally protonated. At a very high pH, the phosphoric acid is totally deprotonated, and everywhere else in between. At a pH of about 5-ish, then I have a whole bunch of this and very little of this. At a pH of about 7 something, I have a 50-50 mixture of this one and this one. At a pH of about 9.5, this stuff goes to nothing. This stuff's also nothing. And this stuff has gone to maximum. At a pH of about 14, this stuff comes all the way down, and I have only PO43-. I could say more about that, but so I can read the intersection points. The intersection here is pKa1, so if my pH is 2 here, then my Ka must be 10 to the negative 2. And if my pH is about 7 something here, my Ka2 must be 10 to the negative 7 something. Okay, that's all I'll say about that one. And I'm almost done, because what else can you say? I mean, you can go into some calculations. I really hesitate to do that. I'm really hoping you'll just think about the buffer region of a weak acid being titrated by a strong base, and that halfway point. So half of 50 is 25, come to 25, up to the curve, and the Ka for this acid must be about 10 to the negative 5. And I've covered that on different videos, so I'm going to stop. Yay! Stopping! Shutting up! The video ends! Yay! I'm getting a bit punchy talking to my computer on a Friday afternoon, let me tell you.